So, what if you could build an artificial intelligence, not with mountains of data, but with the pure, elegant power of logical rules? Today, we're going to unpack that very idea, a really foundational paradigm of AI that takes a completely different path to creating intelligence.
To get started, let's kick things off with a huge question, one that's driven AI research for decades. It's not just about crunching numbers. It's about something way more human, the ability to reason. I mean, how do you even begin to teach a machine to think?
Well, the approach we're exploring today is actually surprisingly direct. Instead of trying to mimic the super messy wiring of a human brain, this paradigm builds thinking machines from the clean, clear principles of formal logic itself.
Okay, so before you can build any complex system, you need a solid blueprint, right? In the world of automated reasoning, that blueprint is a formal system we call first-order logic.
You can think of first-order logic, or FOL, as you'll hear it called, as the official language of logic for a computer. It gives the machine a super strict grammar and meaning so it can understand concepts without any ambiguity. It's kind of like a programming language, but for reasoning.
And calling it the workhorse is no exaggeration, believe me. FOL is the absolute foundation for any AI system that wants to operate based on logical deduction. It is the engine that makes this whole idea of rule-based intelligence even possible.
And that's the million-dollar question, isn't it? Having a language for logic is one thing, but how do you get a computer to actually use it? That's where we need a specific programming approach.
This brings us right to logic programming. This is where the abstract theory of logic meets the practical world of writing code. Now, in most programming, you give the computer a step-by-step list of instructions on how to solve a problem. Logic programming completely flips that on its head. You don't tell it how to do something, you simply tell it what is true by defining a set of rules and relationships. So, how does this actually work? Well, you start by building a knowledge base of rules and facts. The system then uses a process called logical inference to reason over all that knowledge. This whole approach is famously used in languages like Prolog, and the end goal is often to build what we call expert systems. The process itself is just beautifully simple. First, you feed the system knowledge, all your facts and rules. Then, you ask it a question. And finally, the program does all the heavy lifting, using logical deduction to find an answer that's consistent with everything you told it.
All right, so we have our blueprint, first-order logic, and our method, logic programming. Now let's look at the classic tool that's used to put it all into practice.
If you've ever dipped your toes into the world of logic programming, you've almost certainly bumped into Prolog. It literally stands for Programming and Logic, and for decades, it's been the go-to language for bringing this whole paradigm to life.
So what's the secret sauce that makes Prolog work so well? It uses a special format for its rules called horn clauses. You can think of these as these optimized little building blocks for logic, and they let the Prolog engine make deductions incredibly quickly. They're really the reason this theory can be turned into a fast, practical tool. Okay, we've got our blueprint, our method, and our tool. So what's the final product? What are we actually trying to build with all this stuff? The end goal here is often to create what's called an expert system. Now, this isn't some general, all-knowing AI, not at all. Instead, it's an AI with really deep knowledge in one specific field. Think of it like an expert in medical diagnosis, using its rules to suggest illnesses based on symptoms, a lot like a human doctor would.
And these systems can be surprisingly nuanced. I mean, the real world is rarely black and white, and expert systems can actually account for that. They can handle uncertainty, which lets them reason with information that isn't 100% certain. And that is a huge step toward mimicking the intuition of a real-world expert.
So for our last step, let's just zoom out for a second and see where this entire approach fits within the broader landscape of computation. You see, logic programming isn't out there on an island by itself. It's part of a bigger family of approaches that see logic as a direct model for computation. Another example is something called rewriting logic. Both of them share this fundamental belief that you can build computational systems directly from the principles of logic. So, if there's one key thing to take away from all this, it's this direct line from the abstract principles of formal logic straight to a functioning, intelligent system that operates entirely on rules and deduction. It's a remarkably direct and powerful way to build AI. And that leaves us with a final and pretty provocative thought to chew on. Today, AI is just dominated by machine learning models trained on these massive data sets. So, in this new world, What role is left for an approach built not from data, but from explicit, human-crafted logical rules? That's a question that gets to the very heart of what we want artificial intelligence to be.